Sometimes you get graphs with error bars on each point like this. And in this case, you can use line of best fit to determine the gradient or y-intercept and so on. But there is a different approach that you can take when you have error bars like this. Okay, instead of drawing the line of best fit, you can draw the steepest line like this. Okay, so in this case, the steepest line, a lot of students think that is determined by the bottom left point and the top right point. But as you can see, it's not the top right point here that's determining how steep this is. It's actually the one just before that, the second last point there. So you need to make sure you're within the error bars there. You're drawing the steepest line, but you have to be within the errors. Okay, then the shallowest line can also be drawn. In this case, it's the second point and the last point that are determining how shallow it can be. Okay, then you get 2 points from the line like this, and you can find the steepest gradient for this case. So you get change in y over change in x, and I'm converting the y from millimeters to meters. And then I can do the same for the shallowest line, taking 2 points on the line, get the shallowest gradient here. Okay, then I can use this equation here to find the gradient of best fit. So it's just the average of the steepest and the shallowest. So add them together, divided by 2 to get an average here. Okay, and I can also find the absolute uncertainty. That's the advantage with having the steepest gradient and the shallowest gradient. I can find the absolute uncertainty, the gradient, by doing the steepest minus the shallowest. So basically the range divided by 2. So I'll take the large gradient, subtract it, and then here's divided by 2 to get the range here. And I can express my final result with an absolute uncertainty. And you can use this approach for intercepts as well. So in this case, I'm interested in the y-intercept. So I'll draw the steepest line, and the intercept there is 6.4. I'll draw the shallowest line, just making sure that I'm staying within the error bars there, and that gives me 5.60. Then I can find the best intercept by just doing the average of those two intercepts. Okay, so add them together, divided by 2. So that gives me 6.00 volts. Okay, and then I can find the absolute uncertainty. So that's the advantage with having these error bars. I can find the absolute uncertainty in my intercepts and my gradients. So to find the absolute uncertainty, you do the largest minus the smallest. Okay, basically the range, and then divide that by 2. Okay, so here I'm getting plus or minus 0.40. Okay, so here's a graph with errors in both the y-axis and the x-axis. This is a bit more complicated, but it can be used in a similar way. As long as you're drawing lines within the errors, you're fine.